All right, you should have picked this up. A technician using an ultrasound at a frequency of that really big number to scan a heart. The way if I remember tonight, I'll look for my Doppler, my ultrasound thing I have at home. The wave reflects off the organ coming back to the receiver in a very, very, very short amount of time. The speed of the wave in the tissue is 1,540 meters per second. All right, so our formula is velocity equals frequency times lambda. Now, I'm going to be using a shorthand on this. That is because I suck at counting zeros. You can just count your zeros because you're not necessarily going to get my shorthand, but for every 3 zeros, I just put a little line so that I don't have to think. I don't like thinking too much. It hurts. So I'm going to do velocity equals frequency times wavelength. 1,540 is my velocity. My frequency is 2500 plus 3 zeros times my lambda. So I'm going to take 1540 divided by 2500. 1, 2, 3. See, notice I did put in all the zeros. And it gives me a wavelength of 6.2 times 10 to the negative fourth. So 6.2 times 10 to the negative fourth. Wavelength is in meters, so that is in meters. All right. The second one asks, how far did the wave travel to the heart? One of the first formulas we learned about in physics was velocity equals distance over time. In this case, I want the distance. Why am I talking over you? Thank you. I want the distance, not the velocity. So I'm going to multiply both sides by t to get me velocity times time is equal to my distance. I can just fill it in. 1540 times 0.03896 1540 times 0.1234386. It's going to give me a distance around 0.06 meters, which would make sense because your heart isn't hopefully, very far from the outside of you, depending on where you're putting that Doppler. So 0.06 meters. Yeah. No big deal. Not super deep, and they don't ever go because you got bone right on the top. Can't go through the bone, so they usually kind of go like claw around things. So, any questions about that? All right. So the first thing we're actually gonna do is a lab. Let me get this good. All right, so funnily enough, at my Walmart, I could not find match cars for nothing. So I needed more cars, so I have some dyno monster trucks that we're going to use, or a matchbox. So every group is going to get one car, and you're going to get we should have enough for 3. Shoot for 3 different sized sound waves. They should be different colors, but like my kids were helping me last night. I don't pay them, so I'm not going to say that craftsmanship was like their highest priority, okay? So, put 3 rings around my car. Now, these rings are the sound that my dinosaur produces. Let's say he's like a really cool, awesome cop car. This would be his siren. This is his sound wave, and it's emitted on all sides at this frequency. Remember, frequency is what we hear as pitch. So a higher pitch has a higher frequency. Okay, so this is him in his siren. I don't even know what sound a police makes because it's been so long. Knock on wood. So this is where you gotta start. And it tells you to make a dot on your desk. You can use your calculator, you can use your pencil, a water bottle, a frame of reference, or you can make an actual dot if you have your own dry erase markers. I could not get to the supply cabinet this morning and grab a handful. So we're gonna do what we got. So every group needs a car, some sound waves, and a paper. Okay, groups are going to be made up of 2 to 3 people. And you need 1 piece of paper per lab group. You're going to write everybody's name on it who contributed. Does anyone have any questions about this? You're going to go through there. You're going to answer the questions, but this is going to be your initial setup. I'm going to set a timer for 15 minutes. So the cars and the paper are right over there in front of the printer. And these sound waves are over here on the floor. Please be nice to my sound waves.
This paper?
Nope. New paper. Yep, go. Oh, I promise you it does not matter.
You already know.
Frequency. It's a number of waves in a second. We measure it in hertz. All right, so we're going to leave that there for a second, and we're going to talk about what you saw or should have seen. No, seriously, I just opened. Okay. Did not like my restart option.
The Doppler effect. In Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, I love the Big Bang.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it, they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of the road.
Don't stand in the middle of the road.
That's you. And the car drives past you very fast. As it does so, it honks its horn because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look at your...
We're going to do a light one later when we cover light next unit, so we don't need that. But that's what you should have seen, is that As the car got closer to your point of reference, the waves kind of bunched up, and as it got farther away, you saw them decrease in frequency. This is again why the ambulance, the siren makes a different sound as it goes past you. It's one sound that's emitting, but because of this Doppler effect, it's same with police sirens. Hopefully, as the cop goes past you, you're going to hear a different sound. If it pulls up behind you and stays there, you're not going to hear that different sound, unfortunately. The other term that we need to make sure we're clear on is period. Period, because why not, is abbreviated with a big T. This is the time it takes to complete one complete wave. Now, they are related because period is equal to 1 over frequency, or frequency is equal to 1 over period. All right, does anyone know what that behavior is in that first picture?
Oh, it's the
Diffraction. It's diffraction. What's going on with it? What happens? It gets altered?
The walls, they change their shape to go through that little thing.
So the wave shape changes around a barrier. Okay, reflection or an echo. I'm going to draw 2 examples of it. First one would be like reflection of yourself in a mirror on the ground or something. I don't know why your mirror's on the ground, but I'm not here to judge. Second one would be my bat. Emits a sound. Beep, beep. That's a moth. It's food. And those sound waves bounce back towards him. So they're reflected.
What is that?
Some food. Bat food. It's a moth. Dragonfly. I don't care. It's food. Cicada. This is obviously a bat. I don't know. Obviously. Huh? Do bats eat rats?
They're like the size of rats, aren't they?
It depends on the species. Most of the bigger bats are fruit bats. I can't recall. I'm not saying they don't, but I know that like flying foxes and stuff, like the really big ones, they're like this big. Those are all fruit.
Hey, can you make one of those in your bed, like flying squirrel?
Yeah.
Are those like houseable animals?
I mean, in Texas, yo. I mean, they kind of smell bad. But I mean, you do you, man.
Yeah, I want to get a ferret.
Woo, they do. I've had 2. So reflection or an echo is when the wave bounces off something. I'm not going to do what the worksheet wants me to. So we're going to cross that one off. You gotta get me some new whiteout. The next one I want to actually do is refraction. which I should have changed colors for. Now it's going to bother me, but we're here for it. Okay, refraction is what's going on in my window over there with the prisms of light. If you pull back the mirror, I have a film over there that puts little prisms on the ground. It is also seen very commonly in my cup of water with a straw, and it doesn't look like it lines up. It's a funky looking straw, but we're here for it. Okay, this is because the wave bends due to a different medium. Medium, yeah, what the wave travels through. So in this case, to see the straw, the wave is traveling through air, but it hits the water, and now it's traveling through water, so it's going to affect kind of the shape and the velocity and the frequency and all the good stuff. So we pick that up as it's kind of off. That's a bad tuning fork.
Are tuning forks used for like anything, or they're just like
Musically,
demonstrate?
I think you can use them musically to make sure something's on pitch. Okay, that's supposed to be a glass. All right, so resonance is a natural vibration. And so here I have my two badly drawn resonances of tuning forks. But if they were both at the same frequency, the vibration of one could cause the vibration of the other. Or my opera singer breaking the glass.
Did anyone else try to do that when they were a kid?
Did it work?
Yeah,
The one I spent more time than what we actually need to talk about is where you fill up the glasses with different amounts of water, and then you wet your finger, and you can get the glass to vibrate at a certain frequency, and it makes a sound. You know, no? You're looking. No? Okay, we'll watch it. Any glass will work. I'll show you a video of someone else doing it because I couldn't get it to work. All right, waves add up. What type of interference is that? Constructive or destructive? Constructive. Going to increase that amplitude. So you'd have one wave plus another wave equals a wave of a larger amplitude. Okay, destructive interference. You have two waves, and they kind of cancel each other out. You can have both in the ocean. Yeah, so you can have both in the ocean. Depending on how they hit, if they're hitting at the same angles or what. I don't know why I drew that there. I meant to write decreased amplitude. Purple, blue. And what is this last one? Doppler effect. It is the change in frequency of a wave due to motion of a source. Change in the frequency of a wave due to the motion of a source. Any questions? You should have picked up your review. We're at 5.0.